Hello everyone and welcome to today's video on top 10 most important algorithms for coding interviews. Have you ever heard of 80-20 rule, which is also known as Pareto's principle? You might be wondering why I'm bringing this up. Well, it turns out that 20% of algorithms are frequently asked by 80% of the companies. And 80% of the problems you will encounter are based on these 20% of algorithms. This insight is particularly crucial if you are aiming for a software developer position. Now today, I have handpicked the 10 most crucial algorithm questions that fall within this critical 20%. The ones you are mostly likely to encounter during coding interviews. If you want to boost your chances of acing the coding round, then make sure you watch this video until the end. Now let's dive in and get you prepared to tackle those interviews with confidence.
Craving a career upgrade? Subscribe, like, and comment below. Dive into the link in the description to fast-track your ambitions. Whether you're making a switch or aiming higher, Simplilearn has your back.
Just a quick info, guys. Simplilearn has got full stack program in collaboration with IBM. In this course, you are going to learn the MERN stack technologies. You will learn technologies such as MongoDB, Express.js, React.js, Node.js, plus Git, HTML, CSS, and JavaScript to build and deploy interactive applications and services throughout this course. So hurry up now and join the course. The course link is mentioned in the description box. Now before we move on, let us discuss our agenda for today's session. So guys, we are going to cover questions from arrays, string, sorting related algorithms. Then we will move to searching, recursion or backtracking, then greedy related algorithm. Towards the end, we are going to focus on trees, dynamic programming, graph related, and divide and conquer algorithm. So let's get started. So guys, let's start with our first problem. That is trapping rainwater problem. The trapping rainwater problem is a classic example that illustrates how to effectively use the two-pointer technique to solve a problem with both time and space efficiency. Now, what is a given question? So guys, the given question is that find the maximum amount of water that can be trapped within a given set of bars where each bar's width is 1 unit. So consider an input array where you have the height of the bars at 7, 0, 4, 2, 5, 0, 6, 4, 0, 5. So you can see in this diagram, I have illustrated that. Now, the thing is like here is, the essence of this problem lies in understanding that the water trapped above any given bar is dependent on the tallest bars to its left and the right. Because the water will naturally settle at the lower elevations between the taller elevations. The essence of the problem lies in understanding that the water trapped above any given bar is dependent on the tallest bars to its left and right. Because water will naturally settle at the lower elevations between taller elevations. So the first approach is kind of an intuitive approach, and I will tell you that in this approach you should not go for it. So our approach is you apply your intuition, okay? So guys, initially one might think of iterating over each bar, okay? So iterate over each bar from here to here to here to here, and finding the tallest bar to the left and right of it, and using the smaller of these two heights to determine the water trapped above the given current bar. But there is a problem with this approach. Here, the time complexity will become O of n square. It's very much, and it's like a quadratic time square. You're getting a polynomial time basically, and we don't want this. This is very much inefficient for large arrays. Okay, so we have a problem with this approach. It is basically inefficient if our arrays become too much large. Now, what we are going to do, guys, we are going to try an optimal approach. So the technique will be two pointers. So let's proceed. So in the two pointer technique, it offers a linear time solution by O of n. Okay. So our approach to solve this problem would be two-pointer technique. And here our time complexity would be linear, which will be of O of n. And here's a step-by-step solution. So what we are going to do, we are going to initialize two pointers, the left and the right. And they are initialized at the start and the end of the array respectively. So suppose if this is our array, so we can initialize one pointer here and one pointer here. Okay. Now, these pointers will move towards each other. So this thing you have to notice. So the motion will be like this. And until they meet. So we have to declare certain variables such as left max and right max. We can create two variables. The first one will be left max and the second one would be right max. And these are basically used to keep the track of maximum heights encountered from left and right sides of the array as we iterate. In the second process, what we are going to do, we are going to iterate and calculate the trapped water. Here the idea is to move the pointer either to the left or to the right, which is at the smaller height. This is because the water trapped at a position is determined by the shortest height that can hold the water. And it is also influenced by the shorter of the heights at the two pointers. So there is a condition for this. So condition would be something like this. So if height of left is less than height of right, okay? Then we process the left pointer. If the height of left is greater than or equal to the left max, we update the left max to the height left, since no water can be trapped on a bar that is taller than its previous max. Now, if the height of left is less than the left max, then calculate the trapped water as left max minus height left. And we can add this to the total trapped water. Then we again move the left pointer one step to the right, or else process the right pointer similarly. In a similar fashion, we are going to update the right max and calculate the trapped water, like if height of right is less than the right max. And we are going to move the right pointer. And we are going to repeat this process until the left pointer surpasses the right pointer. Now, we are going to see its code and we are going to understand this. But before that, let us try to take an example and understand much more better way. Now, let me take an example and explain you that. So suppose if I say consider this array, okay. So we have an array, something called as 7, 0, 4, 2, 5, 0, 6, 4, 0 and 5. Okay, so we have two pointers, one I have initiated here and one I have initiated all over here. Okay, this is our given array. Now, as the pointer moves towards each other, so what will happen? So when the left max is 7 and the right max is 5, okay, let us declare the variable. So left max we have given as 7 and right max would be equal to 5. So here, what is the height? So the left pointer is at index 1 and height 1 is equals to 0, basically. So the trapped water here will be, this will be 7 left max minus 0. Okay. So now we calculate the trapped water, which is equals to 7, the left max, and this will be minus 0. So it is going to come around 7 units. Okay. I'll repeat again. So here what I'm saying is, when the left max is 7 and the right max is 5, and we know that our left pointer is at index 1. So we are taking it as height of 1, which is basically equals to 0. Okay. So what is the trapped water? So when we are calculating this, we are basically doing a subtraction of the left max minus the height at the index 1. Now, this approach systematically reduces the problem space while calculating the exact amount of water trapped efficiently, and it is particularly suited to problems where solutions depends on comparison between elements with forward and backward dependencies within the array. So, as I have told you earlier, now let us calculate the trapped water step by step. So if we try to see at index 1, okay, so here left equals to 1 and right is equals to 9. So height would be of left equals to 0 less than height of right, which is basically equals to 5. Now, since we have to say that the left max is what? 7, and it is greater than height of 1, which is basically 0. So our trapped water will be left max minus the height of 1, which is equals to 7 minus 0, and it is equals to 7. So at the first we calculated this. Now what is the total trapped water? So T trapped, we can give this variable, and which is equals to basically 7 units. Now we are going to move left to index 2. Okay. Now at index 2 in the step 2, what we are going to do? So here left is equals to 2 and right is equals to 9. So height of 2 or height of left we can calculate equals to 4, which is greater than height of right. Pretty fine, which is equals to 5. Now here what we are going to do? So we are going to calculate the left max, okay, and this will be 7, and this is greater than height of 2, which is basically 4. Now what will the trapped water, guys? Very basic. So our trapped water would be, it would be left minus, or we can say left max minus height of 2, which is how much, guys? 7 minus 4 equals to 3 units. Got it? So now if we here calculate at the step 2, how much is the total trapped water? It will come around 7 plus 3, which is equals to 10 units. Now this was our step 2. Now after this, what we are going to do at the next step, our index would be 3. Okay. Now here our left is equals to 3 and right is equals to 9. Pretty fine. So you can keep seeing the array and how I am doing the calculation. So based on this algorithm, if we are able to calculate it, you will see while we are going to code, it will become much more easier. So let us calculate at index 3 first. So left is equals to 3 all over here and our right is equals to 9. So what we have to calculate, guys? We have to calculate the height. So height of left would be what? It would be 2, and this is greater than height of right. So which is equals to 5, and now our left max would be what? Would be 7, which is greater than height of 3. You can do something like this, and which is basically 2 units. So what will be trapped water all over here? It would be around left max minus height of 3, which will be 7 minus 2 equals to 5 units. So now let us calculate the total trapped water. So T trapped, and this is going to 10 plus 5 equals to 15 units. So you can see it's overall an iterative process. Then again at step 4, we are going to move our left to index 4. Pretty fine. Now at this step, what we are going to do, calculate the same stuff. Like, so here our left would be what, guys? 4, and right would be 9. So we are going to calculate height of left, which is equals to 5, and it is greater than height of right. which is equals to 5 minus left max, and which is basically 7 all over here, and it is greater than height at 4. Basically it's 5. So what will your trapped water in this case? So guys, trapped water will be left max minus the height at 4. Equals to 7 minus 5, 2 units, and the total trapped would be, we are just going to add this, so it would be 15 units plus 2 units, 17 units. Okay, so this is the overall approach for calculating the trapped water. And when you have done it, so guys, you have to keep iterating like this, and at the 7th step, when you are going to add the overall water, it is going to come around 25 units. So basically it's a 2-pointer approach, and the algorithm, as I have clearly mentioned you, and you have to follow certain like this. Now let us see how we are going to code this in Python. So guys, I'm going to use Google Collaboratory for the same, and let us try to understand the code all over there. So guys, in this problem, our algorithm approach was very simple. What we did basically, we initialized the left max and the right max arrays. Then we updated the left max I as a maximum left of max of I minus 1. And we have calculated height of I for each bar. Similarly, we fill the right max array starting from the end of the array. And to find a trapped water, we iterated through the array and computed the sum using the formula water plus equals to min of left max I, right max I minus height I. Okay. So similarly, we were calculating that using the 2-pointer approach. Now, let us try to understand what will be its Python code. So for example, I would say, so we have defined a function named as trap that is going to take a single argument height, and which is a list of integers representing the heights of the bar. Then we are doing the base case check. So if not height, then we are returning the 0. This function first checks if the input list is empty. If it is, then the function returns 0 because no water can be trapped if there is no bars. In the third step, we are doing the initialization. So left, right equals to 0, len of height minus 1, okay, which is very easy. Then we are also going for left max, right max, and we are calculating that using height of left, height of right, and water trapped. So these are all being initialized equal to 0. Pretty fine. Till here, initializations we have been clear. So guys, left and right pointers are initialized to the start and end of the list respectively, or an array. So left max and right max are used to track the maximum heights encountered so far from the left and the right sides as we traverse the list. Water trapped keeps the cumulative total of water trapped. So in the main loop, what you are going to see? So when I have written when left is less than right, this loop continues until the left pointer is less than the right pointer. This loop iterates through the list and moving the pointers inward based on the relative heights at the left and right. So if the height at the left pointer is less than height at the right pointer, then we are calculating this. So if height left is less than height right, and if height left is greater than or equal to left of max, then we are putting left max equals to height of left. Otherwise, we are putting water trapped plus equals to left max minus height left plus 1. So this is an overall formulation which we are basically doing. What this piece of code is doing. So don't get terrified by the piece of mathematical equation. The same way which we have calculated by taking an array earlierly, the same thing which we are doing right now. This block basically is updating the left max if the current bar is taller than the previous left max, and if it is not, it is calculating the trapped water above the current bar. So left max minus height of left, and it is adding to water trapped. The left pointer is then incremented. Now, if the height at right pointer is less than or equal to height at the left pointer. So guys, as you can see in the code, next part revolves around else. So if height of right is greater than or equal to of right max, then we are printing right max equals to height of right. Or else water trapped plus equals to right max minus height of right. And we are subtracting this with 1. And finally, we are returning the water trap. So this block is basically updating the write max, and if the current bar is taller than the previous write max, it is calculating the trapped water above the current bar, which is write max minus the height of write, and it is adding to the water trapped, the same way as we have calculated. And here the pointer is then decremented. So you can see write equals to -1 is given. Now finally, we are returning the water trapped, and after this loop completes, the function returns the total amount of water trapped as it is calculated in this. So now we have taken a given array. So guys, let us try to run this code. So you can see it is giving the total trapped water equals to 25, as I have already told you based on my calculations. So this was a program for calculating the trapped water, and this is a very amazing problem, and it basically gives you an idea regarding how you can use the two-pointer approach. Now let us move on to our next problem. Now guys, we are taking a string related algorithm, and we are going to tackle a problem which is going to ask you to validate an IP address. So let us see what the program is. So the program is write a program basically to validate an IP address. And I have given a definition all over here according to Wikipedia that IPv4 addresses are canonically represented in a dot decimal notation, which consists of 4 decimal numbers and each ranging from 0 to 255, separated by dots, something like 172.16.254.1. So what are IPv4 addresses? Basically, IPv4 addresses are canonically represented in a dot decimal notation, and it consists of 4 decimal numbers. So from a range of 0 to 255, and they are separated by dots. So when validating IPv4 addresses, it's crucial to identify which strings conform to the IPv4 standards and which do not. Here, we are going to clarify the criteria that makes a string a valid IPv4 address, and those that result in it being invalid. So following the explanation, I'm going to provide a systematic approach to solve this validation problem. Now, so what's the criteria for a valid IPv4 address? An IPv4 address must have the following criteria. The first one is 4 numeric octets. Okay, so it should have 4 numeric octets. An IPv4 address is composed of 4 numbers, and we call it as octets, and these are separated by dots, something like 192.168.0.1. Now the range of each octet, if we discuss about, so each octet must be a decimal number ranging from 0 to 255. And the numbers outside this range are recorded as invalid because 256 is not a valid octet. Okay, so when I say 256, this thing you should remember. Now, no leading zeros. This is our third criteria. As they can imply an octal number. However, the single zero by itself is allowed. For example, I'll tell you that 192.168.01.1. This is actually invalid. And if we say 192.168.0.1, this will become valid. So I have told you no leading zeros should be there. Now, what is the exact format if we talk about? The address must strictly follow the number.number.number format, like this. And any additional characters are incorrect placements of dot results in an invalid address. Suppose if I say 192.168.0.1 or 192.168.1.1. So these are basically invalid. So let me give you those addresses. this will become invalid. So I have said you the criteria for determining what is a valid IPv4 address and what is not. Now let us try to code this problem, and we are going to systematically validate this problem. We are going to split the string, and then we are going to solve this problem. So let us proceed to our Google Colab and see the program. So basically all over here what we are doing, so we are splitting it using the split function to divide the address into parts based on dots, and we are ensuring that exactly 4 parts are returned, otherwise the address is invalid. Then we are validating the each octet. We are converting the part to an integer and confirming that it lies between 0 to 255 range. And finally, we are returning the result. So, as you can see all over here, in the first part, I have written def validate IPv4 IP, parts IP.split, then parts equals to IP.split, and here this code is there, and at the end, I am returning if part is not equal to 0, then part.strip 0. So let me explain this code, basically what I'm doing it. So guys, this IPv4 function is basically checking all the rules, okay? And it is checking whether given IP address is valid or not based on splitting it. And finally, what we are basically doing, we are basically doing a string manipulation. So validate IPv4 is designed to check that if a given string conforms to IPv4 address format or not. So the first thing that we are doing, we are defining validate IPv4 IP, okay? Then in the next, we are splitting the strings into octet, where parts equals to IP.split. Now the IP address string is split into parts using dot as a delimiter, and the split method breaks the string at each dot, and it is returning the list of substring octets. For a valid IPv4 address, this list should contain exactly 4 elements, each representing 1 octet. Now finally we are checking the number of octets. So in the code, if length of parts not equals to 4, we are returning it false. So basically this line is checking if the list parts has exactly 4 elements. If there are more or fewer than 4 parts, the function immediately returns false, indicating that the string is not a valid IPv4 address. Now finally we are validating each octets. So here the loop iterates over each element or parts in the list of part, and each part corresponds to one of the octets in the IP address. And finally we are checking the numeric value and range. So if not part is digit or not 0 less than equal to in part less than equal to 255, basically we are checking range all over here, we are saying that return the false. So within the loop, each octet part is checked to ensure that part is digit, means the method we are using is digit method is verifying that the octet contains only numeric characters which are essential for it to be a valid number. So in part lies between 0 and 255. Okay, basically checking the octet when converted to an integer, it should be valid within a range of 0 to 255 inclusive. And the values outside this range are not a valid IPv4. And finally, we are checking for the leading zeros. So here, if part not equal to 0 and part is strip, here 0 not equals to part, then we are returning the false. So basically, this line is checking the leading zeros in each octet. Okay, and part not equal to 0, this condition allows the single 0 as the valid octet, but it is triggering the check for other cases. If I say part is strip 0 not equals to part, the isStrip method removes the leading zeros from the string, and if the result is different from the original part, then the original has leading zeros. And this is invalid unless the octet is exactly 0. And finally, we are returning the true for valid IP address if it is there. If all the checks are passed for each octet, then we are returning true, otherwise false. So I have given a certain IP address. Let us try to run this code. And we can see for the first one, it is saying true. And for this one, it is saying false. Okay. So in this way, you can check for different numbers. So this is basically an idea for checking whether a given string is a valid IPv4 address or not. Now guys, let us move to our third problem, which is related to sorting algorithm. So guys, the question is as follows. So it says, given an integer, sort its element by the frequency and index. If two elements have different frequencies, then the one which has more frequency should come first. Otherwise, the one which has less index should come first. So guys, how we are going to approach this problem? So suppose we have this input element, okay, say 33118368, and we are expecting its output as 331. So basically what we are printing all over here. So guys, we are printing it with the element which has the more frequency. So you can see in the output list we have 33118867. Now let's try to understand the problem first. What it is trying to say. So we want to sort this array so that the numbers with the higher frequencies come first. And if two of the numbers have the same frequency, then the one that appears in the original array should come first. Now let us analyze its two cases, the worst case scenario and the best case scenario. So in the worst case scenario, all the elements are unique. So here, sorting by frequency does little to change the relative order of the elements. Since each has the same frequency of 1, I would say. So we say the frequency of 1, okay? And here the sorting will primarily rely on their original indices, okay? So we are taking two ideas all over here. So basically, sorting is relying on their original indices. Now, let us take an example all over here. So say we have nums as a given list, and here we have 5, 1, 6, and 7. So here all the elements have a frequency of 1, okay? So we can just, and sorted by the index, implicitly the output will be 5, 1, 6, and 7. Okay, if we are sorting by the index. Now here no reordering is needed based on the frequency. Now let us take the best case scenario. So here all the elements are same and the array is already sorted by the frequency, and the index doesn't matter because there is only one unique element. For example, let us take an array of nums equals to 2, 2, 2, and 2. So here what we can notice that all the elements have the highest possible frequency, which is equal to the length of the array. So here the output will be typically, it is going to be 2, 2, 2, and 2. Now let us take the third type of scenario, which is a typical scenario. So let us try to return the original example and break it down to step by step. So suppose we have this array 2, 3, 2, 4, 2, and 3. Okay. Now step 1 would be what? Frequency and index tracking. So at the step 1, we are going to target the frequency and index tracking. So first we need to count the occurrences of each number and track the index of the first appearances. So let us try to notice the frequency all over here. So say 2 3 times, then 3 is 2, then all over here we can see 4 is 1. And if I talk about the first of the indices all over here, so I can take a note of this all over here. And if we talk about first indices, we can say 2 is there of 0, 3 is there of 1, 4 is there of 3. Now in the step 2, what we are going to do? So basically we are going to sort, okay? So here we'll be sorting basically, and we need to sort the numbers based on their frequency, means descending, and by their first index ascending. So if the frequencies are equal, the sorted order will be based on the rules. So it will be 2, 3, and 4. Now we can say that 2 comes first, is of highest frequency, then 3 comes next to it, and then finally we have 4. So 4 comes last. Now what will be step 3, guys? Step 3, we are going to reconstruct the array. So using the sorted order and frequencies, we reconstruct the array. So we can see here, 2 has appeared 3 times, 3 has appeared 2 times, 4 has appeared 1 time. So resulting the sorted array would be two, 2, 2, 3, 3, and 4. So when analyzing the time complexity and space complexity of this algorithm, which we are using to sort an integer array by frequency and then by index, it is very important to consider the component of the algorithm. So if we talk about the time complexity, guys, so the frequency and index tracking we are doing, this step is involving iterating through the entire array once. So for each element, operations are performed that are constant in time. So here the complexity would be O of n, okay, and where n is the length of the array. Now if I talk about sorting, guys, okay, so the array is sorted in based on some custom key, now which involves sorting based on the frequency and which is retrieved in constant time from a dictionary and then by the first index. So we are using a Python sort function typically, which is time sort, okay, which has a time complexity of O of n log n in the worst case. So here, in terms of sorting, we can see we have a time complexity of O of n log n. And this is the worst case. That's the most important thing to remember right here. So combining these predominant factor, so here's the overall sorting step, and we are making an overall time complexity of this algorithm by, so overall if you see, it becomes O of n log n. Now let us discuss about the space complexity. Now 2 dictionaries are used, one to store the frequency of each element and another to store the first occurrence. In the worst case, where all the elements are unique, both dictionaries have n entries, and we have the complexity of O of n, where n is the length of the array. Then we will talk about the sorting space. The space required for the sort operation itself, which for the time sort, involves an auxiliary space. So in the worst case scenario, the complexity, talk about space complexity, it is going to be, in the worst case scenario, O of n. But in practical scenarios, especially for a partially sorted data, it can be pretty much less. So we can take this into consideration. So given these consideration, the overall space complexity of this algorithm is O of n, accounting for the storage of 2 dictionaries and the potential space for sorting operation. Now, we will be using dictionaries, okay, to solve our problem, and the use of dictionary is going to allow for faster lookup operations, which are essential for sorting criteria, hence the space trade-off. The sorting step, while the efficient with a complexity of O of n log n. Okay, and it is the most time-consuming part of the algorithm. The space required for sorting can vary, but the use of dictionary is a fixed cost based on the number of unique elements in the array. So guys, let us see how we are going to write this code in Python based on the same algorithm that I have told you. So guys, as you can see, this is a Python code for our given problem. So you can see here, I have used sort by frequency and index as a function. This function is basically used to sort nums, which is an array of integers. Then I have initialized the dictionary, which is frequency equals to empty dictionary. Now this dictionary is basically used to keep the track of how many times each number appears in the array. Now we have also initialized another dictionary, which is first index. This is used to store the first occurrence of index of each number in the array. Then we are trying to populate the dictionaries. So you can see there is a for loop which iterates over the nums using enumerate to get both the index and the number. Now if a number is encountered for the first time, it's added to both the dictionaries. So frequency is initialized to 0 and immediately incremented. And first index is set to the current index. So if a number is not new, only its frequency is incremented. Now we are sorting the array. The sorted function which is used basically to sort the nums array. And the key for sorting is a lambda function that is basically returning a tuple. You can say frequency bracket x, first index x. So basically this is a tuple which ensures that sorting is primarily by frequency in the descending order due to the negative sign. And the second place by the first occurrence of the index in the ascending order. Now finally we are returning the sorted array. So this function sorted nums, which is the array sorted according to the specific criteria. Now the time complexity, as I have told you, is O of n for populating the dictionaries, and for sorting it is O of n log n. And we have also discussed about the space complexity, which is O of n, where n is the length of the array for storing the frequency and index information. Now let us try to run this code and see whether it's giving the right answers. So you can see we are getting 444662. So which is definitely a correct, because the way we have devised our algorithm outputs this answer. I hope so you would have got a brief idea regarding this. Now guys, let us move to our fourth question, which is searching in a nearly sorted array in a logarithmic time. So let us see what the question is. So it says, given a nearly sorted array such that each of the n elements may be misplaced by no more than one position from the correct sorted order. Search a given element in it efficiently and report if the element is not present in the array. So guys, if you say nums is an array like 2, 1, 3, 5, 4, 7, 6, 8, 9, and we say the target is 5. So the output should be element 5 found at index 3. So guys, given a nearly sorted array such that each of the n elements may be misplaced by no more than one position from the correct sorted order. Search a given element in it efficiently. Report if the element is not present in the array. An element at index I in a correctly sorted order can be misplaced by plus minus 1 position. It can be present at index I minus 1 or I plus 1 in the input array. For example, let me show you what I mean to say. Such that if we say we have 2, 1, 3, 5, 4, 7, 6, 8 and 9. And we say that our target is equals to 5. Now guys, what we want to output that element 5, okay, we have to give that this is found at index 3. Now we are going to start with a numerical specific example to explain the modified binary search in a nearly sorted array. And then we are going to analyze the complexities. So let us consider another array. Say, let us take a small case, okay? And we say we have this array 3, 5, 2, 10 and 6. So guys, in a perfectly sorted order, the array would something look like this. So we say nums equals to 2, 3, 5, 6 and 10. Okay. But however, each element in the nums can be misplaced by no more than one position from its correct sorted order. For instance, the element 2, which should be at index 0, it is at index 2. Now, what is our task? So for example, we are going to search the element 10 in the array nums. And then we are going to apply the modified binary search approach. So what's the algorithm for the same? So the step 1 would be initialization, okay, in which we are going to start with left equals to 0 and right equals to length of the array minus 1. Then we are going to do the binary search with the adjustments. So here we are going to calculate the midpoint. Okay, so we'll say the midpoint of the given array, so which is going to be left plus right divided by 2. Okay, then we are going to check 3 positions to account for potential misplacements. Okay, so here will be nums mid minus 1, then we'll have nums mid and nums mid plus 1. Now, depending upon the comparison between these positions and target value, we are going to adjust the left or right pointers. What will be the next step? The next step would be checking for conditions. Now, here we are going to say like if nums of mid, okay, is a target, if this is equals to target, then I will say return index. We are going to also check if mid is greater than left. Okay, so we're going to also check all over here that mid is greater than left, and if nums of mid minus 1 is the given target, so that we can handle the misplacement to the left. Okay, basically we are doing this to handle the misplacement to the left. Now we are going to check, okay, again, that if mid is less than right, so we are going to say if nums mid plus 1 is our given target, we are going to handle its misplacement to the right. Now we are going to adjust in the next process. Okay, the left and the right pointers based on the target number is greater than or less than nums of mid. So this adjustment you have to do. You have to adjust the target number. You have to check that it is greater than nums of mid or it is less than nums of mid. So we have approached till here. Now let us take an array and let us try to apply with this operation. So here we have the example execution. Like suppose if our array nums, here we have 3, 5, 2, 10 and 6. So what we are going to do, we are going to search for 10. Okay, so let us say, let us search for 10. Okay, now we are going to start with 0. So we say left equals to 0 and right equals to 4. So in our first iteration, okay, what we are going to do, we say that our mid that we have calculated equals to 2. Okay, and we also see that nums of 2 equals to 2. Okay, just note this. Now we are going to check, okay, here the check is going to come, that nums of 2 and nums of 1 and nums of 3. So we say that nums of 3 matches the target. Okay. Then we are going to return 3. So this is how this approach works, basically. And now let us discuss the time complexity, which is very important. So suppose you are appearing for an interview and you are applying this approach. So you have to understand that time complexity of applying this approach is O of log n. Okay. So Because the modifications to the binary search do not change the logarithmic reduction in the problem space at each step. Now we are checking the immediate neighbors like mid minus 1 and mid plus 1, and it only adds a constant time operation within each iteration of the search. If I discuss about the space complexity, guys, then the space complexity is O of 1. And as per this algorithm uses a constant amount of space regardless of the input size, with just a few additional variables for indexes and the midpoint calculation. This approach effectively adjusts a traditional binary search to accommodate slight unsortedness in the array, which provides an efficient solution for searching in a nearly sorted arrays. And this ensures that search process remains robust even with minor deviations from the complete sorted order. Now let us see the Python implementation of the same problem. And we are going to use the same IDE, that is Google Colab. So guys, as you can see this code, so we have all over here a function which is search in nearly sorted. So it basically takes an array nums and a target value to find. Then we are doing the binary search adjustments. So you can see there is a while loop and it continues as long as left is less than equal to right. Then we are doing the mid calculation. So basically it finds the middle index. After that, we are doing a direct check. It is going to check whether the element at the mid index is the given target. Finally, we are going to go for the neighbor checks. Additionally, like we are checking for mid minus 1 and mid plus 1 to account for potential misplacements. So guys, these checks ensure that slight unsortedness of like plus minus 1 position that is handled. Then we are going the pointer adjustments. So it says if nums of mid is less than target, then we are adjusting left to mid plus 2. And skipping over the mid plus 1s since it was already checked. Now we are also taking this condition that if nums of mid is more than the given target, then adjust the right to mid minus 2. Similarly, skipping the immediate neighbor. That's why I have taken mid minus 2. And finally, I'm returning the return minus 1. So if the loop exists without finding the given target, then it just returns minus 1, indicating that the target is not in the array. Same as guys. So this is the overall manipulation that we have done. Now you can see this code all over here. So initialization is this part, then here the conditional is there. Then we are checking the mid position, checking the left neighbor, checking the right neighbor. Then we are moving the pointer based on the value comparisons. Okay. Now we have taken an array and we say the target is 10. Now let us see whether this gives us answer 3. So you can see we are getting answer 3. So with this approach, we are able to solve this problem. Now let us move on to our next question. So guys, I hope so you would have heard about Hamiltonian paths. So basically it is related to a graph problem. Okay. So let us see what the given question is. By seeing this diagram, you have got some idea regarding what could be the Hamiltonian graph. But first of all, let us try to understand what is our question. Our question is, given an undirected graph, print all the Hamiltonian paths present in it. And the Hamiltonian paths in an undirected or a directed graph is a path that visits every vertex exactly at once. So a bit of definition I have added all over here. Now, so if I say that you are given an undirected path, then print all the Hamiltonian paths present in it. The Hamiltonian path is an undirected or a directed graph is a path that visits each vertex exactly once. For example, following the graph shows a Hamiltonian path. Okay, so as you can see in this diagram, okay, all over here. So in this way, some kind of Hamiltonian path is there. Now, how we are going to solve this problem? And here we are going to use a recursion or use a backtracking. So basically on the first, I'm going to try for the backtracking. Okay, so here is your undirected graph. Okay, now we are going to check that if every edge starting from an unvisited vertex leads to a solution or not. As an Hamiltonian path visits each vertex exactly once, we take the help of visited array in the proposed solution to process only unvisited vertices. And also we are going to use the path array to store the vertices covered in the current path. If all these vertices are visited, then a Hamiltonian path exists in the graph and we print the complete path stored in the path array. Now, what we are going to do basically, So let us take a graph as a Hamiltonian graph. Let me take a graph all over here. So say we have a graph. Okay, let us take a graph. Say it is equals to okay 2, 3. Then at 2 we have 1, 3 and 4. At 3 we have 1, 2 and 4. At 4 we have 2, 3 and we are closing it. Now it is a simple undirected graph where we can say that the vertex 1 is connected to the vertex 2 and 3 and vertex 2 is connected to vertex 1, 3 and 4. Okay. Similarly, vertex 3 and vertex 4, all their connectivity is given in this array. Now this graph contains several Hamiltonian paths. A Hamiltonian path is a path that visits each vertex exactly at once. So for example, a possible Hamiltonian path in this scenario could be like so here we could have say 1, 2, 4 and 3. So we are going to start with vertex n, then travel to vertex 2, then to 4 and then to 3. So example I would also give like for a non-Hamiltonian graph. So we can consider a graph structure where it's not possible to visit each vertex exactly once without repeating. So say we have this kind of graph. So say we have graph n, okay, and it has 1 of 2, 2 of 1, 3, 3 we have 2, 4, then we have 4 which is 3. So guys, this is a simple path graph and it does not contain a Hamiltonian circuit. And depending on the starting point, it may not always form a Hamiltonian path. So we're going to start at vertex 1 of 4 and move through the vertices in a sequence, and we have a Hamiltonian path all over here. 1, 2, 3, 4 or 4, 2, 3, 1. Okay. So guys, if we start at vertex 2 or 3, we cannot form a Hamiltonian path that visits every vertex once without retracing the steps. Therefore, this given graph is not qualifying under these conditions. Now, let us try to understand the Hamiltonian path finding algorithm. So guys, to find all the Hamiltonian paths in a graph, we can use backtracking approach. Okay. So our approach will be backtracking. Now initialize. So initially what we are going to do, we are going to initialize. Okay. So we are going to start with the vertex and make it mark as visited and initialize the path with this vertex. The next would be a recursive search. Okay, in this we are going to explore all the adjacent vertices. For each adjacent vertex, if it is not visited, then we are going to add it to the current path and mark it as visited. Then at 3, we are going to recurse with new path. And finally at 4, we are going to backtrack it by removing the vertex, okay, and from the path and making it as unvisited. Now at step 3, it will be completion, which would be if the path include all the vertices in the Hamiltonian path, then you can print or store the path. If you're not getting that, you can continue exploring the potential paths by backtracking. So this overall approach is backtracking, and this is a Hamiltonian path finding approach. So basically when the problems are related to graph, we can use these techniques and to find the required vertices which are connected to all the vertices. Now it's a very amazing problem. It's more of a mathematical problem, but Also, it is in conjunction with the computer science. Now, let's try to solve this problem using Python. Now, you can see all over here, we have defined the Hamiltonian path graph. So, here you can see what are the parameters, the graph, the current vertex, paths visited, and result. Now, let us try to understand each part one by one. So, for example, first let us discuss the time complexity of this. So, the time complexity is O of n, where n is a number of vertices. So, basically it is n factorial. Okay. So in the worst case, we explore every permutation of the vertices. Okay. Now, the space complexity is O of n due to the recursive call stack and additional data structures to keep the track of path and visited vertices. So here the provided Python function Hamiltonian path is basically designed to identify all the Hamiltonian paths in an undirected graph using a recursive backtracking approach. Now, first you can see we are defining a function. Okay. Then there is a graph, a dictionary will be there, which is representing the undirected graph where the keys are vertex, identifiers, and values list are adjacent vertices. Then there is a current vertex where the vertex currently being visited in the graph. Then there is path, a list that keeps a track of vertices in the current potential Hamiltonian path. Then there is a dictionary that tracks whether each vertex has been visited. It basically helps in preventing revisiting vertices and thus ensures that each vertex appears exactly once in the path. Then there are results, a list to accumulate all the Hamiltonian paths found. Now we are taking the base case for recursion, where you can see all over here that if the length of the path is equals to length of the graph, okay, then what we are going to do, basically we are appending and we are saying path.copy and return. So basically this function checks if the length of the path equals to the number of vertices in the graph, and if it is true, it means that the path contains every vertex exactly once, constituting a Hamiltonian path. This path is then added to the result list. The path.copy is used to append a snapshot of the current path, ensuring further modifications to the path do not alter the stored path. Then there is a recursive exploration all over here. Then if we talk about recursive exploration, then for neighbor in graph, we say there is a current vertex, and if it is not visited by the neighbor, we say that visited neighbor equals to true. Then we are appending path.append the given neighbor. There is a Hamiltonian path where we say graph, neighbor, path, visited results, and we are basically popping it up. Then we also say that visited neighbor equals to false. And this block of code basically is handling the recursive exploration. We are iterating over the neighbors, like for each neighboring vertex, what we are doing, we are saying that the current vertex, the function that checks if it is not being visited, it is marked as visited and we are using the recursion. If the neighbor hasn't been visited, it is marked as visited and it is added to the path. And the function recursively calls itself to continue building the path from the new vertex. Then basically we are doing the backtracking. Okay. So in backtracking, what we are doing, we are removing the last added vertex from the path and marking it as unvisited. So this step is very crucial as it allows for exploring alternative paths that includes different sequences of vertices. Now finally, the end of the function. So the function doesn't return a specific value since it modifies the results and directly stores all the Hamiltonian path. When we talk about the execution flow, guys, the Hamiltonian path functions is expected to be called initially with the starting vertex, an empty path, a visited dictionary initialized to false for all vertices, an empty list for the results. From there, it explores all the possible paths recursively using backtracking, and it is used to navigate through the search space of vertex permutation that could form a Hamiltonian path. Now, to use this function, you can initialize a graph. Like here, I have initialized a graph all over here, and basically I'm trying to find all the Hamiltonian path. So basically what this program is going to do, it is going to start the search from vertex 1, but then you could start from any vertex and expect it to find all the Hamiltonian paths in the graph. Assuming that you adjust initial call parameters accordingly, the output will be list of lists, where each inner list is representing a different Hamiltonian path found in the graph. So let me run the code and show you. So you can see it has printed all the required Hamiltonian path. So this completes our objective of this program. Now let us proceed to our next problem. Now, our next problem is job sequencing problem with the given deadlines. So let us see the problem. So it says that given a list of tasks with deadlines and total profit earned on completing a task, it says find the maximum profit earned by executing the task with specified deadlines. Okay. Now you can assume that each task takes 1 unit of time to complete and a task that cannot execute beyond this deadline. Also, it says only a single task will be executed at a time. So, for example, you can say there's a job ID, profit, and a deadline. Okay, so let us try to add something. So, guys, say if we choose task as 1, 3, 4, 5, 6, 7, 8, and 9. So, we can achieve a maximum profit of say 109. And we are also noting that the task 2 and task 10 are left out. So we can see the task deadline for here and the profits such as 1, 9, 15, 2, 2, 3, 5, 18. And with respectively, it would be there. Now, if you see this diagram, we can see that for this given problem, we can see there is a job ID, there is a profit, there is a deadline. Now, how we are going to execute this problem? So the idea is like if we want to solve this problem, we can approach a greedy approach, okay? And the idea will be pretty simple. You can consider each task in the decreasing order of their profits and schedule it in the latest possible free slot that meets its deadline. Very simple. Now, if no such slot is available there, then don't schedule that task. So here you can arrange it. So for example, so guys, as you can see all over here, I have taken the given task. Here is a deadline, here is a profit. So I've just exaggerated these numbers. And as you can see all over here, the task 5, okay, has a maximum priority associated with it, has a maximum gain of 30. Okay. Similarly, we can say the task 4 has a least priority. So we are going to apply the greedy approach, in which what we are going to do, we are going to consider task in the decreasing order of priority. So if we talk about the deadlines and profits, so maximum is going to come first. So 5 will be there for 25, 6, 2, 20, 3, 18, and this. So let me write it again. So on the first order of priority, it would be 5. Okay. Then it will be 4. Then 25, 6, 2, then it will be 30, 20, 3, 5, 18, 1, 9, it will be 15, next, then it will be 9 again, then it will be 4, 12, 8, and next would be 7, 10, 7, 5, 8, then there will be 10, 3, 5, 2, then there will be 2, 2, 4, and 7. And finally, we are going to get 1. So guys, we are going to demonstrate the greedy approach. So let us consider deadline in the form of a circular structure. So here what we are going to do, we are going to build a task. So guys, in this approach, what I'm going to do, the first thing is I'm going to sort tasks by profit. Okay. So what will happen at this stage, where all the tasks are based on their profits in descending order? It is going to ensure that we are considering the most profitable tasks first, and it is a key to maximizing the total profit. Then we are going to initialize the data structure. So use an array or a list to keep a track of the scheduled task, and if the size of the array should be equal to the maximum deadline from your task list. Third, what we are going to do, we are going to do task scheduling. Now we are going to iterate over the sorted list of the task, and for each task we are going to attempt to schedule it as close to the deadline possible. We are going to start from the task deadline slot and move backward to find a free slot. If a free slot is available, then we are going to schedule the task there. and it is going to ensure that each task is scheduled in a way that leaves a room for tasks with earlier deadlines. And finally, we are going to calculate the total profit. Now, once all the tasks are processed, we can calculate the total profit from the scheduled task. So let us try to implement it in Python. Now guys, you can see all over here, we are defining a function called max profit, and here we are taking an argument called task. Now next process is, we are sorting a task by profit descending. So we are using a lambda function all over here. So here task.sort key equals to lambda x and x2. Then the tasks are sorted in a descending order based on profit. This sorting is crucial because the greedy algorithm prioritizes the higher profit tasks to ensure that they are considered first. This maximizes the total potential profit that can be secured. Then finally, we are initializing a scheduling array. Okay, you can see all over here where we are putting the max deadline equals to max of task 1 for task in task, and we are saying schedule equals to none multiplied by max deadline plus 1, and we are also initializing total profit. So we can see that in the max deadline, it is determining the maximum deadline from all the tasks to define the size of the scheduling list. It basically represents the latest time slot available for a scheduling task. And you can see the schedule all over here. So it is an array which is initialized to none. So it is sized according to max deadline plus 1, which is including slot 0 and which remains unused, assuming task deadlines start 1. Then there is total profit, which is initialized to 0. And this variable will accumulate the profit from successfully scheduled task. Then you can also see all over here that for scheduled task, we are taking for task, deadline, profit in task. And for D in range, deadline 0 and minus 1. So if not scheduled, we are checking if slot is free. Then we are putting schedule D equals to task profit. And we are saying that total profit plus equals to profit. And we are breaking it. So basically what happening in this block of code, that the outer loop is basically iterating through each task, now ordered by descending profit. And the inner loop looks for a free time slot to schedule the current task starting from its deadline. And it is moving backwards. So this is to place the task as late as possible without missing the deadline. So leaving the earliest slots free for other tasks that might not need them. So if a free slot is found, okay, the task is placed, and in this slot, and its profit is added to total profit. This loop basically breaks as soon as the task is scheduled, which ensures that each task is considered only for scheduling. And finally, we are returning the total profit. So after all tasks have been considered, the function returns the accumulated total profit, which is the sum of total profits from all the tasks that was successfully scheduled within their deadlines. Now, we have taken all these tasks and we are basically printing the maximum profit with respect to task. So you can see the tasks are defined in the list of tuples where each tuple contains the task number, its deadline and its profit. And the max profit function is called with this list. So the maximum possible profit is printed. If we talk about its complexity analysis, then primarily complexity driver is the sorting operation, which is O of n log n. And there is subsequent nested loop which runs in O of n of d, which is the worst case, where n is the number of tasks and d is the maximum deadline. If we talk about space complexity, guys, it is O of d, where d is the maximum deadline due to the space required for the schedule list. So guys, this code effectively schedules a task to maximize profit using a greedy algorithm. Ensure that most profitable tasks are given priority while respecting their deadlines. Now let us move on to our next question. So guys, our next question is based on determining whether a given binary tree nodes are cousins of each other or not. So let us go for that. So guys, as you can see all over here, it says that given a binary tree, determine if two nodes are cousins of each other or not. Now, two nodes of a binary tree are cousin to each other if and only if they have different parents, but not at the same level. So guys, to clarify the concept of cousins in a binary tree, let us consider a specific binary tree example and identify which nodes are cousins and which are not. We are going to examine a binary tree structure and use to determine its cousin relationship. So for example, here you can see this structure. So say we have 1, 2 and 4 and 5, 3 is given to 6 and 7. So let us talk about their nodes and relationship. So at the level 0, node 1 is the root. Okay. At level 1, node 2 and 3 are the children of node 1. At level 2, nodes 4 and 5 are the children of node 2, and node 6 and 7 are the children of node 3. If we talk about cousins, guys, nodes are that on the same level but have different parents. So here example, node 4 and 6 both are on the level 2. 4 is the child of 2 and 6 is a child of 3. Since they have different parents, they are cousins. Now next is nodes 5 and 7. Both are on the level 2, where 5 is a child of 2 and 7 is a child of 3. These nodes are also cousins for same reasons as 4 and 6. Now, if we take about non-cousins example, you could see nodes 2 and 3. Both are on level 1 but share the same parent 1. They are siblings, not cousins. Now, similarly, node 4 and 5. Now, let us check programmatically how to check the cousin status. We are going to code this program in Python. So guys, you can see this program, and let us try to analyze this program, that how we are locating whether given nodes are cousins of each other or not. So you can see in the first lines of code, we have created a class called treeNode, and we are initializing def init self x. Now here we are allocating self.val equals to x, self.left equals to none, self.right equals to none. Basically, it's defining a simple tree node class for binary tree nodes, where each node has a value val, a left child left, and a right child right. Now you can see there is a isCousins function. Okay. Now here def isCousins root x and y. This is the main function that checks if two nodes x and y are cousins in a binary tree rooted at root. Now next step, we are finding the depth. Okay, so define find depth and parent node. So we have taken node val depth 0, parent equals to none. So if not node, we are returning none. So if node.val equals to val, we are returning depth and parent. Finally, we are returning find depth and parent, where node.left val depth plus 1 node, or we are finding depth and parent node.right val depth plus 1. This is basically a recursive helper function which is searching for a node with a given value val in the tree. It returns a tuple containing node's depth and its parent code. It traverses a tree starting from the given code node and checks if the current node is target, so node.val equals to val. So if so, it returns the current depth and parent. And if it is not found, it recursively searches the left and right of the subtrees, incrementing the depth with each recursive call and updating the parent to the current node. In the next step, we are basically checking cousins condition. So we have xinfo equals to find depth in parent. We're taking root x, and there is yinfo where we are finding depth in parent root y. So if xinfo and yinfo are there, then x depth x parent equals to xinfo y depth. It is assigned to xinfo. Similarly, y depth y parent is assigned to yinfo. And basically, we are returning x depth equals to y depth, and x parent is not equals to y parent. If we are not getting this, we are returning false. So basically, this piece of code retrieves the depth in parent information for node x and y using a helper function. If both nodes are found, then we are saying that xinfo and yinfo are not none. It is basically unpacking this information into depth and parents for each node. It is returning true if both nodes are at the same depth, okay, and have different parents, like x parent is not equals to y parent, which are the conditions for nodes to be cousin. If either of the node is not found, then it is returning false. Guys, the time complexity of this is approximately O of n. And the function find depth and parent is basically a depth first search. That may be, in the worst case, visit every node in the tree once, where n is the number of nodes in the binary tree. So if we talk about the space complexity, so due to recursion, the space complexity is determined by the height of the tree edge, as that is the maximum size of the call stack. In the worst case, for a skewed tree, it could be O of n. So guys, the code efficiently checks if two nodes are cousins by determining their depths and parents through a DFS approach. It ensures that the nodes are met the specific criteria of being at the same level but having different parents, effectively solving the cousin determination problem in the binary tree. So guys, this was a solution. Now we have given our tree all over here. Now let us try to run this code and let us see what is our answer. So you can say this is true and this is false. So our objective is completed all over here. Okay guys, let's move to the next problem, that is a subset problem. And this problem is basically based on dynamic programming. So guys, the question is, given a set of positive integers and an integer k, check if there is any non-empty subset that sums up to k. So for example, if I have the input 7, 3, 2, 5, 8 and we say k equals to 40, then we want an output with subset with the given sum exists. So 7 to 5 sums up to 40. So this is our given output. Now a naive solution would be to cycle through all the subset of n numbers and for every one of them check if the subset sum to the right number. The running time of this order is O of 2n.n. Okay. So how this is coming guys? As there are 2n subsets and we can say we are checking each subset, so we need to sum at most n elements. Okay. So if we look at these, so we get O of 2fn. So we can say it is pretty expensive. A better exponential time algorithm uses recursion. Subset sum can also be thought of as a special case of the 0-1 knapsack problem. For each item, there are two possibilities. Include the current item in the subset and recur for the remaining items with the remaining total. You have to exclude the current item from the subset and recur for the remaining item. And finally return true if we get a subset by including or excluding the current item. Otherwise, return false. The recursion base case would be when no items are left or the sum becomes negative. So we have to return true when the sum becomes 0. So the subset can be found. Now, using dynamic programming, so to solve the problem of finding if there is a subset in a given set of positive integers that sums up to a specified integer, suppose k, we use a dynamic programming approach. This method is efficient and ensures that we explore all possible subsets. So suppose we have a given set of integers, say all over here. So we take a equals to 7, 3, 2, 5 and 8. And we take k equals to 40. Okay. So here the task is to determine if there is a subset of A which elements sums up to k. So why are we creating an array of size k plus 1? You can pause the video and think about it. So guys, we are creating an array of size k plus 1. It's a dynamic array because we need to check the sum up from 0 to k. So the index of the DP array which represents all the possible sums from 0 to k. So this allows us to use a Boolean array which has an index of I, which indicates whether a subset of sum of I is possible. Now, what will be the algorithm of this? The first is we have to initialize an array. Okay. Then create a Boolean array DP of size k plus 1. Okay. So we have taken already k plus 1 size and it is initialized to false. Okay. So we are also have to set repeat, then set DP 0 to true because the sum of 0 can always be achieved with an empty subset. In the second process, we have to iterate through each element. Okay. So iteration is there. For each element in the array, update the DP array from the right to left to avoid using the same element multiple times. So for example, say we have the element 7. Okay. So start from back to 14 to the front 7. Okay. So DP 14 remains false. Then we have DP 13. This is also false. Then we have all over here 12, 11 similarly, and 9, 8, 7. Repeat. Okay. Similarly, we have 12, 11, 10, 9, 8, okay, and till 7 we have to go. So here it will be false, okay. This will also be false. Now guys, still here we are having a false. Now when it comes 7, it becomes true. Now we can say 7 plus 0 equals to 7. Now after this, you have to update the DP array. Okay, so it would be true, false, false, and similarly it's gonna go till false. Now element 3, let's look for element 3. Okay, so if we are taking element 3, then start back from 14 to the front of 3. Okay, so in this scenario also we have DP of 14, this will also be false. Similarly we have 13, then we have 12, 11, 10 and 9. So when it comes till 9, we will find that it becomes true. Why guys? Because 3 plus 6 equals to 9 and DP of 8 remains false. Okay, so we can say that DP of 6, okay, basically is true all over here because we have updated this value in the earlier section. So guys, this will become true. Why guys? Because as we know that DP of 6 was true, so 3 plus 6 will be equal to 9. Now similarly DP3 is also true because 3 plus 3 equals to 6. Okay. DP of 5 will remain false and DP of 4 also will remain false. Finally, DP of 3, as I have told earlier, will become true. And after this, you have to update the given array. So I hope so you have got a brief idea regarding this. So you have to continuously do this and keep updating this array. Okay. So guys, when the DP array has already covered all the values from 0 to 14, it cannot change further. So you'll do a final check since we know that DP of 14 will become true. So it confirms that there is a subset that sums up to 14. Now let us see the Python code and let's try to understand this. So guys, let us try to understand this code. So we have implemented this using Python. So you can see there is a function which is subset sum. It is going to check if there exists a non-empty subset of a given set A that is summing up to a given integer which is equals to k. Now we have defined def is subset sum A and k. Then we have initialized our DP array. So initially it's false and it is multiplied by size of the array which is k plus 1. Now we have initialized DP of 0 equals to true. After that we are proceeding for initialization where a boolean array of DP size k plus 1 is created and it is initialized to false. Now DP of I will be true if a subset with some I is possible using the elements from the set A. So here DP of 0 is set to true because the sum of 0 can always be achieved using an empty subset. Now after this, what we are doing guys, we are updating DP array for each element in A. So you can see I have written for num in A, for I in range k, num minus 1 and minus 1. If DP of I minus num is there, then DP of I is true. Then we are updating the DP array and the outer loop is iterating through each element num in the given set. And here the inner loop iterates backwards from k down to num. This is ensuring that each element is used only once. If DP of I minus num is going to check if a subset sum of I minus num is achievable or not. And it is achievable, then by adding num to this subset, a subset of I will also be achievable. And hence DP of I will be set to true. Now we have given this given example as a 73258 and k equals to 40. Now we are using this function to check whether there is a subset available which is going to sum up to 14. Let's try to run this. So you can say it is returning true because in here you can find that subset exists which is going to sum up to 14. So guys, this was a given implementation of this problem. Now let's proceed for the next problem. Now here, as you can see from this diagram, that we are going to apply the Dijkstra algorithm. So let us see what is a given question. So guys, the question is, given a source vertex S from a set of vertices V in a weighted graph where all its edge of weight U and V are non-negative. So you have to find the shortest path of weights D and S V from the given source S for all the vertices present in the graph. Now we can see all over here that suppose I give you the vertex and the minimum cost. Now let us try to imagine the route. Okay, say for going A to B, okay, this is our given route. And if I talk about the cost, it is 4 units. Okay. Now this is the minimum cost. Now we can go this by A to E, then to B, and A to C. So for this, the cost is equals to 6. Now, after going from here, A to E, to B, to C, then we are going from E to D. Okay. So here we can say the cost is 5. Then we are going from A to E to D, then A to E, and we can find the cost is 3 units. Now we all know that this is a given base problem which I have given you all over here. So with the minimum cost and the given routes which we are traveling on. Now basically you need to understand first what is a weighted graph. A weighted graph is a graph where we are adding the units all over here. Like suppose from A to B, so this is the given weight for that. Then A to E to B have given the cost as 6. So similarly for this scenario, we are going to use breadth first search, which can be used to find the shortest path in an unweighted graph or even a weighted graph for having the same cost of all of its edges. But if the edges in the graph are weighted with different cost, then BFS or breadth first search generalizes to uniform cost search. So instead of expanding nodes to their depth from the root, uniform cost search expands the node in order of their cost and from the root. So a variant of this problem is a Dijkstra algorithm, and we can apply to solve this problem. Dijkstra algorithm is an algorithm for finding the shortest path between nodes in a graph. So for a given source node in a graph, the algorithm is going to find the shortest path between that node and to every other node. And it can also be used for finding the shortest path from a single node to a single destination node by stopping the algorithm once the fastest route to the destination node has been determined. Dijkstra algorithm is based on the principle of relaxation, in which more accurate values gradually replace an approximation to the correct distance until the shortest. Distance is reached, the approximate distance to each vertex is always overestimate of the true distance, and it is replaced by the minimum of its old value with the length of a newly found path. It uses a priority queue, guys. You have to remember, if you are using a Dijkstra algorithm to solve this problem, then we have to understand we have to use priority queue. Okay. Now, it is queue to greedily select the closest vertex that has yet not been processed and performs this relaxation process of all the outgoing edges. Dijkstra algorithm is a fundamental algorithm for finding the shortest path from a single source vertex to all the vertices in a graph with non-negative edge weights. It is particularly well suited for graphs represented as weighted graphs or directed graphs. So let me try to explain you once more. So suppose we have vertices A, B, C, D and E, okay? And say we have edges with weight all over here. So for A to E, I say the weight is 3. From E to B, say the weight is 1. From B to C, the weight is 2. From E to D, the weight is 2 units again. So if we take the source vertex A, then in this setup, we find the shortest path from A to all the other vertices and understands the route taken. So you can see all over here, there will be a direct route in which not given, hence it will be probably longer than the alternative. And if you're taking an indirect route, suppose we are going from A to E to B, then with a cost of 3 plus 1, okay, which will be 4. So similarly, I have to calculate the direct route and indirect route for each of them. So I have to take these things into consideration. So say, what I mean to say guys, so suppose all over here, A to B. So we can see from in this diagram that there is no direct route present only. So we have to apply the indirect route. So for indirect route, how we are going to go guys? Say, here A to E is given. So first we'll go to A to E, then from E to B. So the overall cost will be 3 plus 1, which will be equals to 4 units. So in similar way, you have to calculate and you have to find out which is the shortest path for each one of them. Let's try to code this in Python. Then you will have a fair idea that how we can solve this problem using Dijkstra algorithm. And we are going to use the priority queue. So guys, as you can see all over here, this is the pseudo code for this problem. So here I have declared a function called Dijkstra, which is taking a graph and a source into consideration. Then I have taken distance of source equals to 0. So this is initialization. And here I am creating the vertex to Q. Okay, let me comment it. Okay. Now, here what we are doing basically guys, that for each vertex in a graph of V, we are finding that if the vertex V is not equal to source, then I'm putting the first distance of V as infinity because it is an unknown distance. And the previous V is also undefined. This is a predecessor of V. Now, here we are going to add with the priority of V, and here we are calculating the distance of V. We are also checking that if the Q is not empty. So we are extracting the minimum, okay, all over here. So here, for each neighbor of V of U that is still in Q, okay, what we are doing basically guys, here we are calculating a distance of U plus length of U in V. And here we are basically checking which is the shortest distance. So if this distance is less than this, alt is less than distance of V, then we are putting distance of V equals to alt, previous of V equals to U, and we are queuing it up with the decreased priority of V and alt. And finally what we are returning an array of distance array and the previous array. This is a basic pseudocode. So you can try this implementation in Python, okay? So you can put a graph all over here, put a source, and try to calculate the minimum distance using the Dijkstra algorithm. So guys, generally in the given exam, they will ask you the pseudocode only. Mostly there are chances. So you can explain something like this. Now let us move on to our final question. So guys, let us look at our question. So the question is, given an integer array sorted using the merge sort algorithm. So guys, how we are going to approach this problem? First, let us have an overview of merge sort. So we all know that merge sort is an efficient sorting algorithm that produces a stable sort, which means that if two elements have the same value, they hold the same relative position in the sorted sequence as they did in the input. In other words, the relative order of elements with equal values is preserved in the sorted sequence. Merge sort is a comparison sort, which means that it can sort any input for which a less than relation is defined. Now, let us talk about how does a merge sort works. We are going to look into divide and conquer algorithm. Like all divide and conquer algorithms, merge sort divides a large array into two smaller subarrays and then recursively sorts the subarrays. Basically, two steps are involved in the whole process. Divide the unsorted array into an n subarray, each of size 1. And then an array of size 1 is considered as sorted. Repeatedly merge the subarrays to produce a new sorted subarrays until one subarray is left, which would be our sorted array. So guys, you can see this is a diagram all over here, which I have showed you earlier. So this is a diagram for sorting the element. So guys, you can see here we are sorting the elements, okay, and there are 7 elements in an integer array. So here you can see it is working on divide and conquer algorithm that works by recursively breaking down an array into smaller subarray, then sorting them and then merging into the sorted subarrays to produce the given sorted array. So as you can see in this, there are 38, 27, 43, 3, 9, 82 and 10 are the elements of the given array. Now step 1 would be dividing the array. So we have divided the initial array, okay. Now we are splitting it into 2 halves. The left half is 38, 27, 43. The right half is 3, 9, 82 and 10. Step 2 will be recursively divide each half. So left half would be left with 38, 27, 43. Then it is split into 38 and 27, 43. If we look at the right half, guys, we can see 3, 9, 82 and 10 are there. We are splitting it into 3 and 9 and then 82 and 10. Step 3 would be recursively divide further until each subarray has one element. So we can see left of the left half has 38 and right of the left half has 27, 43. We are splitting into 27 and 43. The left of the right half 3 and 9 are there. Then we are splitting it into 3 and 9. If we look at the right of the right half, we have 82 and 10. We are splitting it into 82 and 10. Step 4 will be merge the subarrays. So here would be the merge step. So we are merging 27 and 43. Compare 27 and 43, then merge to 27 and 43. At step 10, we are merging 3 and 9. We are comparing 3 and 9 and merging to 3 and 9. Then we are merging 82 and 10. So we are comparing 82 and 10, then merging 10 and 82. Now the merge step with larger subarrays will happen. So we are merging 38 with 27, 43. Now we are comparing 38 with 27, okay, and then 43, which is merging to 27, 38 and 43. Then we are merging 3 and 9 to 10 and 82. Compare 3 and 9 with 10 and 82, merge through 3, 9, 10, 82. And finally, we are proceeding for the final merge. So we are merging 27, 38, 43 and 3, 9, 10 and 2. So finally, we are getting 3, 9, 10, 27, 38 and 43 and finally 82 in our final step. So this is how this diagram is depicted, and I hope so you would have got a brief idea regarding this. Now let us try to implement this in Python. Now guys, let us try to understand the Python implementation of merge sort. So we can see first we have taken the base case where we have the function merge sort, and it is recursively called until the array length is greater than 1. Now if the array length is 1 or less, it is already sorted. Then the next step is dividing. The array is split into 2 halves, left half and the right half. And finally, we are doing the recursive sort. So as you can see guys, all over here, that merge sort is called recursively and it is sorting them individually into halves. Now the sorted halves are then arranged back together. So we have 2 pointers, I and j, which are used to track the elements in the left and right halves respectively. Okay. Now, what we are going to do, a third pointer k is used to place the merged element back to the original array. Now, when the elements are compared in the merged in sorted order, remaining elements from either of the half are copied to the array if any elements are left. Now, you can see all over here that we are checking at this step that if any element was left, so we are deploying this code. While I is less than length of the left half, so we are giving array of k equals to left half of I. And then we are incrementing I by 1 and k plus 1. Now at this, we are checking for the right half. If j is less than the length of right half, then what we are doing basically, we are putting the parameter k. So array of k is assigned to right half of j. And we are incrementing j with 1 and k with 1. Now we are taking the same array and let us try to sort this array. So we have used our function merge sort and we are putting this array as our argument. Let's try to see if this technique gives us the elements in sorted order. So you can see 3 is coming first, then 9, 10, 27, 38, 43 and 82. So guys, the way we have discussed our algorithm, so this code perfectly suits to it. So I hope so guys you have got a brief idea regarding merge sort. So guys, these were the top 10 coding interview questions which you should definitely try practicing if you are planning to appear for a coding interview. That was all for today's session, guys. I hope so. You would have enjoyed our today's video on top 10 commonly asked interview questions for the software engineering role.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.